Go outside tonight and look up. The moon has been there every night of your life. Every night of every life before yours. It should not be there. 4.5 billion years ago, another planet crashed into ours. The moon is what came out of the wreckage. But the planet that hit us never left. It's still here. And you're standing on top of it. Almost everyone knows the first half of that story. A Mars-sized world called Theia hit the young Earth, and the debris became the moon. Almost nobody knows what happened next, because when we finally got moon rocks back and tested them, they didn't say what anyone expected. They broke the theory instead of proving it, and they left one question sitting open for 50 years. If a whole planet hit us, where did that planet go? There are no pieces of it in the asteroid belt. None in any meteorite ever found. For decades, the answer was simply that we didn't know. We may have just found it. Rewind to the beginning, about 4.5 billion years ago. The Earth is roughly 50 million years old. It is not the planet you know. There are no oceans. There is no life. The surface is molten in places and cooling in others. And there is nothing in the sky, no moon, no tides, just a young planet spinning much faster than it does now, in a solar system still crowded with objects big enough to be called planets in their own right. One of them was on a collision course. We call it Theia, after the Greek Titan, who was the mother of the moon goddess. That name is the only thing about it we're confident of. Its size is still argued over. The usual figure is Mars-sized, which means about a tenth of Earth's mass. Some studies push it to 30%. At least one goes higher. Then it hit. The energy involved is difficult to hold in your head. Both bodies partially vaporized. The Earth was left spinning fast, tilted over and wrapped in a disk of molten rock. Out of that disk, the moon formed. For a long time, this was a story with no evidence attached. It was an idea from the 1940s that nobody could test. Then Apollo brought rocks home. And the first thing those rocks told us actually fit. The moon has almost no iron core. Earth's core is about 30% of its mass. The moon's is between 1 and 2%. That's exactly what a giant impact predicts. Theia's heavy iron core would have sunk into Earth. The moon got built from the light stuff, the mantle material thrown clear. So far, so good. The theory worked. Then somebody measured the oxygen. You'd think moon rocks would look like the planet that made them. They don't. Hold that thought, because it's the moment the whole story turned over. We'll come back to it in a minute. But first, something else. In the 1980s, seismologists were doing something completely unrelated. They were timing earthquake waves as they passed through the Earth, using them like an X-ray to map the inside of the planet. And they found two things that shouldn't be there. Two enormous regions near the very bottom of the mantle, sitting right on top of the outer core. One beneath Africa, one beneath the Pacific. Seismic waves slow down when they pass through them, which means they're made of something different from everything around them. They are not small. Together, they hold about 6 times the mass of the moon. Spread across the surface of the Earth, they'd form a layer roughly 100 kilometers thick. Nobody knew what they were. For 40 years, they just sat there in the data, unexplained. Remember them. We're coming back. Now, the oxygen. Here's what should have happened. If a separate planet hit us, and the moon formed mostly out of that planet, then moon rocks should carry that planet's chemical signature. Different world, different fingerprint. Every planet has one. Rocks from Mars are measurably different from rocks from Earth. Meteorites from the asteroid Vesta are different again. Where a thing formed in the solar system is written into its oxygen. So the Apollo samples should have looked foreign. They looked like Earth, not similar, nearly indistinguishable. And not just for oxygen, for titanium, for chromium, for element after element, the moon keeps coming back as a piece of Earth's own mantle. Scientists have a name for this. They call it the isotopic crisis. The evidence that was supposed to confirm the story is the evidence that broke it, because it leaves you with two impossible options. Either Theia happened to have formed with almost exactly Earth's composition, which one study put at under a 1% chance, or the moon isn't really made of Theia at all, and that forced a rethink of the collision itself. The original picture was a glancing blow. Theia clips the Earth at an angle, shears off a spray of material, and most of what ends up in orbit is Theia. That version is elegant. It also produces a moon that looks foreign, which is the opposite of what we measure. So a different picture emerged. Not a sideswipe, a far more violent, far more direct hit. In this version, the two bodies don't just touch, they mix. The impact is energetic enough to vaporize and blend material from both worlds so thoroughly that whatever condenses out is a blur of the two. The moon isn't a fragment of Theia sitting next to Earth. The moon and the Earth come out of the same stirred pot. Some models go further still, into a structure called a synestia, where the Earth briefly isn't a planet at all, but a spinning cloud of vaporized rock with the future moon forming inside it. None of this is settled. The exact geometry is still genuinely argued over in the literature. But every one of the newer models points the same direction. The harder the collision, the more thoroughly Theia gets mixed into Earth rather than flung away from it. Which brings back the question from the start. Go outside tonight and look up, and you're looking at a moon that is mostly made of Earth. So where did Theia go? For a long time, the honest answer was nowhere we can find. Theia should have left traces. It didn't. There is no Theia family of asteroids. No meteorite has ever turned up carrying an unmistakably Theian signature. A planet-sized object hit us and then apparently vanished from the record entirely. The assumption was that it had been erased. 4.5 billion years of a churning, convecting mantle should have stirred any leftover chunk into the general mixture, the way milk disappears into coffee. Then, in 2019, a geophysics student named Qian Yuan sat in a seminar at Arizona State University. The talk was about the giant impact. Yuan didn't work on the moon, he worked on the deep Earth. He worked on those two unexplained blobs. And sitting in that room, he put the two problems together. What if the missing planet isn't missing? What if the reason we can't find Theia in space is that Theia is underneath us? He went looking to see whether anyone had proposed it before. Nobody had. He was, by his own account, worried people would think the idea was crazy. He submitted the paper in 2021. It was rejected 3 times. The reviewers wanted the collision modeled properly. So he found people who could do it at a resolution hundreds of times finer than earlier attempts. The question was whether Theia's mantle material would be dense enough and the impact just gentle enough that pieces could sink to the bottom of Earth's mantle and stay there without dissolving into it. The models said yes. The paper ran in Nature in November 2023. Its argument is that most of Theia was absorbed into the young Earth, sank, and settled at the core. The blobs are what's left of it. The moon is the small remainder that stayed in orbit. Now, a caution, because this matters. This is one study, and it is a proposal, not a settled fact. Other explanations for the blobs are still live. Some researchers argue they're graveyards of ancient subducted crust. Others think they crystallized out of an early magma ocean. And some seismologists question the shape itself, suggesting the neat pile-like structures may partly be an artifact of how we image the deep Earth with low-frequency waves. The blobs are real. What they are is still an open question. But if Yuan is right, we have been walking around on the impactor, which leaves one more thing to correct. You've almost certainly heard that the moon is the reason life here got complicated, that it holds Earth's tilt steady, and a steady tilt gives you stable seasons, and stable seasons gave evolution the calm millions of years it needed. It's a good story. It comes from a real paper published in Nature in 1993, which found that without the moon, our tilt could swing wildly, anywhere from nearly 0 to 85 degrees. It has been argued about ever since. In 2012, a team including researchers at NASA ran the moonless Earth again with better models. They found the tilt wandered much less than that. It stayed within a range of roughly 20 to 25 degrees across hundreds of millions of years. Their conclusion was blunt. A large moon does not seem to be needed to keep an Earth-like planet stable long enough for advanced life. Other researchers have gone further and suggested our moon sits close to the mass where it would start destabilizing the tilt rather than steadying it. So the one thing most people know about why the moon matters may be the least certain thing in this entire video. Go outside tonight and look up. The moon is a little further away than it was last night, about 3.8 centimeters a year, measured by lasers bouncing off mirrors the Apollo astronauts left behind. As it goes, it drags on our spin and the day gets longer. In the age of the dinosaurs, a year held 372 days. And underneath your feet, 100 kilometers of something that may not have started here is still pushing heat toward the surface. Hawaii sits above it. We never found the planet that made the moon. We may have been standing on it the whole time. The story was always there. You just had to look down.
Subscribe to my channel.